Imagine an industrial press slamming down with thousands of pounds of force. In a split second, a worker reaches too far, crossing an invisible threshold. The machine is carrying massive kinetic energy. If it doesn't stop immediately, the impact will be catastrophic. Let's freeze the frame right here. How does this mindless block of steel know it has to stop before it's too late? This is the role of the OSSD, the Output Signal Switching Device. It functions as the digital link between human presence and mechanical force. To see how it works, we have to look at the moments before the incident occurred. This is the on state. The protected area is clear, the wiring is correct, and internal diagnostics show zero faults. The safety light curtain maintains this state by projecting an unbroken grid of infrared beams, constantly monitoring the environment for any interruption. This timing diagram shows the logic at work. As long as the protected field is free, power and the OSSD signals stay on. Notice segment T1. A successful fault check must complete during this window before the OSSD switches on. This verified equilibrium is the prerequisite for operation. The safety loop depends on a digital signal that is designed to drop the moment a single condition is no longer met. Back in the present, the crisis begins when an opaque object, anything larger than 14 millimeters, interrupts those infrared beams. The response is instantaneous. The OSSDs drop their voltage, switching to the off state and triggering an immediate stop command. But safety engineering assumes that components will fail. What happens if the wire carrying that stop command is damaged or cut? To prevent a single point of failure, the system uses two completely separate channels, OSSD1 and OSSD2. A strict wiring rule applies. These channels can never be connected in series or parallel. They must remain isolated. This dual-channel architecture ensures that a single severed wire or an electrical short can never prevent the machine from stopping. These signals feed into a safety controller, which performs two-channel feasibility monitoring to ensure both lines agree. The system also checks itself using test pulses. These are rapid dips in voltage lasting just 300 microseconds, long enough to verify the wire's integrity, but too fast to shut down the machine. All these digital processes happen in milliseconds, and that timing translates directly into the physical layout of the factory floor. Engineers use a specific formula to set the safety distance. It accounts for the OSSD's response time, plus the time the machine needs to physically come to a halt. As a final safeguard, feedback loops monitor the physical valves and contactors. The system needs to see that the mechanical hardware actually followed the digital off command. When the math and the hardware align, the press slams to a rigid halt, stopping just millimeters away from the worker's hand. The accident was avoided, but the factory can't stay frozen. Production needs to resume safely. The restart process depends on why the system stopped. If the halt was caused by a system fault or stray light, the OSSD stays locked until a human investigates and performs a manual reset. However, if the interruption was just a temporary breach, like the worker pulling their hand back, the system can recover automatically. For this to happen, the field must be clear, and exactly 80 milliseconds must pass, shown here as T3, before the OSSD switches back to on. The OSSD is a mathematically precise link. It converts human presence into a command that the machinery cannot ignore.